Well, there it is. Ghosts N Goblins at 60 frames per second, and it only took changing a 3 to a 1. Of course, the timing of the physics is all wrong, and, well, just look at it. But I'm getting ahead of myself. Capcom's Ghosts N Goblins hit arcades in the summer of 1985. Many computer and console ports would follow, and the task of bringing the title to the NES fell upon developer Micronics. Now, we've talked about Micronics in the past, and their titles are known to be rather janky. But the more I look into the code behind the Micronics library, the more I realize that they had some talented developers churning out these games. And perhaps the reason they scored contracts with companies like Capcom was not because of their award-winning high-quality result, but rather because of how they managed to produce something reasonable inside a short period of time. Speed is a skill, because the name of the game has and always will be money. If you're new to Behind the Code, welcome. If you're a veteran of the series, this one is going to be a bit more conversational. Over a period of the last 4 years, we've examined game physics, mapper chips, sound bugs, and more for various titles from the Famicom NES platform. The dive into the control of Ikari Warriors exposed some questionable design decisions for turning the player as well as applying velocity. It demonstrated something that was over-engineered by the Micronics team, and this was a teaser for some of the other tricks they have buried within their development history. There was no cheap, build-your-own Famicom game dev kit and giant manual for anyone to use that wanted to create a game on the platform during the system's heyday. It required homebrew solutions at a company level and leaned upon mastery of 6502 assembly and a familiarity with the Famicom architecture. Learn it quickly. Software developer? More like hardware liaison. If you built a game engine, it was likely made from scratch. Building a second game? Borrow code from the first game. Building a third game? Borrow code from the second game. The game engine evolves over the course of time, perhaps in tandem with the developer's understanding of the platform. Both Micronics' understanding of system hardware and their game engine evolved rather quickly. If you look at the code behind various entries in their catalog, you'll see a lot of shared DNA. But with this continued evolution, each new game entry begins at a fork in the road. Do you apply this knowledge, an evolved game engine, and the skills acquired over time to create even better games, or do you smirk and say, we can develop games even faster now? Which path did Micronics take, and did the road vary from title to title? Their 1942 port from December of 1985 demonstrated some rather beginner-level knowledge of implementing scrolling on the system. If you look at the top of the screen, you can see the new background graphics being drawn after the area they occupy scrolls into view, despite having an entire screen's worth of extra space available to update tiles ahead of time. Yet just half a year later, in June of 1986, Ghosts N Goblins was released on the Famicom and had multi-directional 8-way scrolling. But before we include it on the Micronics Masterpiece collection that everyone has been wanting for decades, there are several elephants in this room. Number 1, the game is janky. Number 2, what is up with this frame rate? And number 3, the sprite system performance is reding-dong-diddly-diculous. Ghosts N Goblins has been mentioned to me several times throughout the history of this channel, and the most common question concerns the frame rate. Is there anything we can do to improve it? Can it be converted to 60 FPS? And the response I provided was speculation. It would take reverse engineering the game, finding areas to gain performance, improving upon that logic, and adjusting the physics to match as we tighten things up. A generic go-to response for frame boosting any given game. But then, one day, I opened up this can of worms. While I may not have a solution, I definitely have the start of one. So let's dive into the Micronics game engine used for Ghosts N Goblins and my journey of reversal so far. First of all, what is the frame rate of this game? The answer is complex. Let's use the event viewer to illustrate video output frames and by extension, the passage of time. In this example from Mega Man 3, a 60 FPS game, all the work for the next game frame is completed in less than the time it takes to draw a single video frame to the television. If logic maintains this rate, every new video frame to the television is also a new game frame, thus a 60 FPS game. But what if you didn't finish the next game frame in time for the next video frame? Performance is now in a pickle. Many games, including Mega Man 3, stall graphical updates for the sake of game logic by drawing the previous game frame to the television yet again as they finish up work. At that moment, the given game is running at 30 FPS. This happens on a case-by-case or frame-by-frame basis. This is not something the NES just does. This is by Capcom programmers' own design and is a fairly common approach used by other developers. If you haven't experienced a game slowing down before, welcome to the NES. Another method is to determine that your game is not going to be 60 FPS and therefore design it to run at a constant lower frame rate, like 30 FPS. Konami did this with TMNT. It splits the CPU work across 2 video output frames. Any graphical updates are held back during the NMI period of the first frame in the pair, just like when Mega Man 3 slows down, and that same video frame is drawn again as work on the new game frame finishes up. The key difference between the two is that Mega Man 3 physics are designed for 60 FPS and the game slows down to 30 FPS or worse when necessary, whereas TMNT animation and physics are designed for 30 FPS and the game just runs at 30 FPS. Now what about Ghosts N Goblins? 3 video frames worth of time are allocated in order to create a new game frame. 1, 2, 3, 1, 2, 3. We appear to have a waltz, or a 20 FPS game. Now we know. I wish I could say, and knowing is half the battle, but the battle has yet to begin. This 20 FPS is not what it seems. TMNT deliberately held back on sending graphical updates to the PPU during the first 1/60th of a second, so it would repeat the previous video frame's graphics to the television as it wrapped up work for the next game frame. You can see identical pairs of frames being output one after the other here. So you might think that Ghosts N Goblins holds back graphical updates during the first and second video output frames, and then sends those updates after the third. Yay, 20 FPS. However, this is not the case. Ghosts N Goblins flutters out new game frames like a wounded butterfly. If you recognize jank when you play a game and can't explain it but would like to do so, you're in the right place. To understand what happens, we need to dissect the game. Since 3 full video frames of CPU time are reserved to create a new game frame, let's map out time by connecting the video frames vertically. Here is our timeline. This will make it easier to tell you when certain things happen across a period of 3 video frames. From this point forward, let's refer to these as sub-frames and label them A, B, and C. Each new game frame is split across this triad, and these letters will make the sub-frames easier to identify. Question: if Ghosts N Goblins does not hold back graphical updates sent between subframes here and here, what updates do we see? Let's dive into the NMI handler logic to find out. Reversal of this area is fun and interesting, and like many other areas of code reversal, starts with speculation and momentary confusion. The good thing is that this code hits up a lot of system hardware specific addresses, and that makes it easier to reverse what is happening. With the NMI handler almost completely reversed, we can see how Micronics prioritizes and handles updating graphics, sound, and reading controller input, among other things. Our particular focus concerns the rate of graphical updates that are sent to the PPU during vertical blank, a time used by the NMI handler. These include tile patterns for sprites and backgrounds that are stored in character RAM inside the cartridge, the graphical contents of the name table, created using background tiles, object attribute memory or OAM contents that hold sprite data, including X and Y position attributes and the tile ID for the graphics pattern, and the colors used in the palettes applied to background tiles and sprite tiles. Seems like a lot of stuff to maintain, and it can be. The implementation of these updates crafts the components of a game engine, and just like a real engine, it works best if the update logic runs like a well-oiled machine. The most basic sequence of how this works is, as the frame is drawn to the TV by the PPU, the CPU performs next frame computations and stores future sprite data, background updates, palette updates, and more in RAM. After the frame is finished being drawn, an interrupt occurs. The CPU uses the time immediately following this interrupt to send all graphical update bytes from RAM to the PPU. The crude explanation is, get it ready here, transfer here. The Micronics implementation has a few quirks amongst these updates, and the Sprite engine is the worst of them by far. Oh, just wait. Back to the NMI handler logic. Because this is a decent chunk of code with a lot of branching and looping, let's describe logic flow using a flowchart. As a reminder, the NMI handler is executed after every subframe. After some of this and some of that to start execution inside the handler, the first major item copies all prepared sprite bytes held in RAM for the next frame to OAM inside the PPU. That's where the PPU stores sprite data. Now this happens during every NMI period. No flags, no conditions, just do it. That's a problem. If sprite processing performed inside game logic crunch time has not completed by the time subframe A's NMI occurs, spoilers, it hasn't, this logic writes whatever it has available at the time to the PPU and inevitably the television when it draws the next subframe. Again, we'll get back to this. The next item in the logic is setting the attribute update flag to 0. This is significant, but I won't explain it until we know more. Next up, we check the flag to see if we need to update an entire row of tiles of the background stored in the name table. When do we need a new row? When scrolling up or down. This flag is likely set somewhere inside the game frame logic responsible for changing the player's location relative to the level. It would set the row update flag so we would know, hey, we need more tiles. If the flag is yes, we copy the row tiles we previously queued up in RAM, because that's where we like to stash things in advance, to the name table in VRAM. In fact, if I walk the logic that copies the tile IDs, you can see each tile updating via little red boxes inside the name table viewer of the emulator. Cool. Two other noteworthy things happen. The attribute flag is incremented to 1, and we clear the row tile update flag because we just did that. Now, if the row didn't need to be updated, we check the column update flag. This is used for scrolling horizontally. Do we need a new column because we scrolled? Yes. Okay, copy the new column of tiles from RAM to the name table in VRAM. Also increment the attribute flag and clear the column tile update flag. If we didn't need to update any column tiles, we fall into checking the need to update the colors for the various palettes. After updating row tiles or updating column tiles, these sections of code also drop down to the update colors check. Notice that row updates have priority. If we update row tiles this time through the NMI handler, we do not update any column tiles. So we only update one or the other. If both need to be updated, column tile updates won't happen until the next time through the NMI handler. So the possible tile updates are no updates, update row only, update column only, update row, and then later update column. Next up is a check to update colors. This is also controlled by a flag. Colors for the palette are updated for different sections of the game. The title screen, ready screen, map, and level screens use different colors. The colors are also updated as you are playing the level, but they are on a scheduled update, at least for the areas I examined. Game logic appears to set the update colors flag to yes every 12 subframes. Just like updating row tiles and column tiles, the logic also increments the attribute update flag. If colors are updated or not, we finally hit the question of updating the attribute table. Ghosts N Goblins' implementation of this is rather odd. First of all, what is the attribute table? The attribute table holds the palette selections that dictate the colors for the background tiles. Tiles are 8 pixels by 8 pixels. One screen's worth of tiles is 32 tiles by 30 tiles. That is 960 tiles. We need 1 byte per tile, so a screen needs 960 bytes. Our name table can hold 2 screens worth of tiles, so we have 1920 bytes to hold all of the tile IDs. VRAM on the NES is 2K in size. That leaves 128 bytes, or 64 bytes per screen's worth of tiles to store color palette information for all the background tiles in VRAM. Wait a second. 960 tiles only have 64 bytes available for storing color palette information? Yes. Each byte can hold 4 palette selections as we only need 2 bits for the palette ID, so that helps a bit. That still doesn't give us a full 960 different palette selections though, does it? We don't have a unique one-to-one relationship between a tile and its palette. A single byte in the attribute table controls the colors for a 32 by 32 pixel area. That's 16 tiles. We know that we have 4 palettes per byte, so the palettes control groups of 2 by 2 tile sets. A palette for the top left, top right, bottom left, and bottom right groups. So the gridlock of NES graphics is perhaps a bit more limited than we thought. The attribute table, color limitations, and the history of trying to work around these limitations is a topic for a separate video. But Ghosts N Goblins has to answer the challenge of updating attribute table bytes to the proper value in order to assign the appropriate colors to the background tiles. It has to do this while possibly scrolling 2 axes at almost the same time. Let's sidestep to a game that has things a bit easier. Welcome to Mega Man 2. Let's see both the tile and attribute updates in the emulator as we scroll. The top window showcases tile updates, and they appear in red. Mega Man 2 appears to perform 16 tile updates per NMI period. You can see those tile updates appear in 4x4 chunks off screen. 16 tiles means 16 bytes sent to the name table. Meanwhile, the yellow tiles here represent updates written to the attribute table. Again, a single byte in the attribute table holds the palettes for 4 2x2 sets of tiles inside a grid. Mega Man 2 was designed to send each background tile update as 16 tiles inside a 4x4 area that conveniently only requires a single byte to set the palette data for that entire grid. Both tile and palette data are written on an as-needed basis. Nice and compact. Now, we know that Ghosts N Goblins pushes either a full row of 32 tiles or a full column of 30 tiles during our NMI update period. So you figure worst case scenario dictates maybe updating the bytes of attribute data that span a row when vertical scrolling occurs. But Ghosts N Goblins doesn't work the attribute table on an as-needed basis like Mega Man 2. It just continuously hammers a quarter of the 128 bytes of the attribute table every single frame. Even if you are just standing still, it just keeps going. Were new tiles written? No problem. The attribute hammer will get around to updating the color palettes momentarily. The irony is that whenever we write a new row of tiles, write a new column of tiles, or hit our frame rule for updating colors, we bypass the attribute update logic. Under default conditions, we set the flag to 0. That means do your big 32-byte attribute right. However, if we make the value anything else but 0, we don't write new attributes that time through the NMI handler. It's a trade-off of CPU time consumed during NMI. Finally, at least for our example, we set the current camera scroll position regardless of if we updated attributes or not. There's more stuff to do after this, such as read inputs from the gamepads and deal with the sound engine, but this covers the bulk of our graphical updates during the NMI period. Ah yes, the Sprite engine. You knew we'd come back to this one. Just how is the performance of the Sprite engine? If we return to the actual Sprite code inside the NMI handler, we can see that it does transfer Sprite data from NES RAM to OAM, Object Attribute Memory, inside the PPU. A single instruction is enough to push all 256 bytes from a single page of RAM to OAM. Ghosts N Goblins does this, but it doesn't just reserve the necessary 256 bytes in a single page in RAM. It reserves double that amount, 512 bytes. That's 1/4 of NES RAM. The question is, why? If we slow the game down and watch the sprite set in OAM, it reverses order every frame. NMI alternates loading sprites into OAM from page 2 in RAM or page 3 in RAM. The reason this is done is because we can only have up to 8 sprites on a single scan line. By effectively mirroring the previous order of all 64 sprites, we reverse the priority of every sprite on every frame. Admittedly, this is an easy way to not have to worry about prioritizing your sprites. If you continue to reverse the order, everything should just work out, right? Well, one side effect of Ghosts N Goblins is that some of the sprites used for an object, such as playable character Arthur, are overlapped rather than adjacent to each other. When you reverse the priority every frame, you reverse the overlap. This leads to some rather interesting side effects as we switch which block of sprite data is sent to the PPU. This is not the only Micronics game that reserves this much room for sprite processing. Super Pitfall, Akari Warriors, and Tiger Heli are a few of the other Micronics-developed games that mirror sprite priority every frame. Are the sprite systems of these games identical, or at least related somehow? Quite likely. We would know unless we reverse engineered all of them. But at the very least, we know we are mirroring sprite priority for all 64 sprites on every frame one way or another. And if we think in terms of the big picture, game logic is timed for 20 FPS, but the sprites are reversing priority at 60 FPS. This may contribute to the jank. Spoilers, this contributes to the jank. It will be easier to explain if we skip out of the NMI handler's push logic for new sprites and reverse the Micronics sprite engine that builds them. Oh, My goodness. Why doesn't Ghosts N Goblins run at 60 frames per second? I'm gonna say because sprites. There is so much code devoted to building sprites that the logic takes almost an entire frame's worth of time to execute. Okay, let's jump over to Mega Man 2 for a moment. This is Woodman's stage. In this frame, we have 1, 2, 3, 4, 5, 6, 7, there's a little caret there, objects on the screen. The NES can only do 64 sprites on the screen at a time, and we've exceeded that number in order to render these objects. Not only is some of Enemy 1 missing, but notice that Mega Man's entire energy bar is gone. Its sprites weren't rendered on this frame. Mega Man 2 runs at 60 FPS. That means with this many objects and no slowdown, we should have completed work for the next frame within 1/60th of a second. And here is the event viewer with the performance breakdown. It took this much time to compute the logic for the next frame, including setting up all of the next frame sprites in RAM, which we know is going to be a fresh full set of 64. The remaining time here is the CPU's execution of an infinite loop as it waits to start work on the next frame. Not bad. The time to execute sprite logic may dominate most of this CPU time, but who cares? We made the deadline. But what about Ghosts N Goblins? I'm going to tell you a story. I'm going to tell you a story using boxes. Our triad of frames. Infinite loop time that we begin to execute after computing the next game frame is represented with pink boxes. All 2K of NES RAM. This is the story of copying bytes for sprites. First of all, each object on the screen has relevant data. What is its X location page integer fraction? What is its Y location page integer fraction? Current pose, action taken, direction faced. There are many traits that need to be tracked, and they are stored down in this area of RAM. I didn't bother to map all locations. Now the sprite builder needs some of this object data, and it shoves a lot of bytes around just to prepare to build sprites. It is arguably a waste of time. The logic pulls each object's status bits, which includes if it's active or not, that's important, Y position integer, X position integer, current tileset ID or pose, and palette set ID. This part of the sprite creation logic might be combined with other processing. I'm not sure because I didn't go back this far in terms of reversal. Rest assured, this takes up a chunk of time during subframe A. Next, sprite logic uses these copied arrays to assemble a sprite creation queue. The status array is checked. If the object should be created, the Y position, pose, palette, and X position bytes are added to the queue for that object. It doesn't take too long to queue objects in the current frame. Next, the remainder of the 64-byte sprite creation queue is filled with FF values. Again, not long. With the sprite creation queue in place, logic then uses that queue to create the sprites inside page 2 of RAM. This process takes that long. No joke, that's a heck of a lot of time to create sprites. Oh wait, we aren't done. We only made 45 sprites. That means 19 slots are unused. Micronics elected to write FF to every single byte that is not used. That takes this much time. Interesting. We were interrupted by the enemy handler time here, and this logic sequence has to execute, and then we resumed writing our FF values to page 2. And as we know, the enemy handler copies sprite data to OAM inside the PPU. But we weren't finished. That can't be good. Anyway, the FF loop completes. Then there's one thing left to do. Copy all of the bytes from page 2 in RAM to page 3 in RAM and reverse the sprite order of those bytes. Let's add that time period to the illustration. So it's going to take about this much time on average to build the sprites during each triad of subframes. And the more you think about it, the worse it gets. Remember that the sprite order is reversed every 1/60th of a second. This is accomplished by constantly changing the location in RAM from where we want to copy sprite data. The origin of the sprite sequence across the subframes could be page 2, page 3, and then page 2, or it could be page 3, page 2, and then page 3. In this example, a copy from page 2 here would manage to get all the new sprite data as it was just written to page 2 in RAM right here. We interrupted the erase the rest code that came after it. So we should be okay, at least in this example. What about a 232 situation? That is a problem. We have not yet reversed our brand new sprites and written them to page 3 in RAM. So that means this logic in NMI copies outdated sprite data from page 3 in RAM to OAM inside the PPU, and then moves the scroll window to the new location. Let me repeat that. NMI handler A sends out old sprite data to the PPU along with a new scroll position. These two things are rendered to the television in the next frame. What this means is that for 1/60th of a second, the level scrolls, but the sprites do not. They're in the old location on the television. But have no fear, you know what's going to happen. As this broken frame is drawn to the television, the CPU finishes sprite engine logic. All remaining sprites in page 2 are cleared out, and even page 3 gets the proper reversal of sprites. NMI handler of subframe B hits. The proper sprites are copied to OEM this time. The scroll window doesn't change because we already did that. And subframe C is drawn to the television. And this time, the sprites are in the proper place. But the damage is done. The sequence went A, B, C. A, B, C, A, B, C, A, B, C. It doesn't matter that 2 of the 3 frames are correct, because the players will just experience jank, jank, jank. And of course, this graphical glitch is inconsistent, because the next triad of subframes will use a different RAM origin sequence for the sprites. So what is the frame rate of Ghosts and Goblins? I would say 20 FPS with a bad case of hiccups. Physics run at 20 FPS. Sprite priority runs at 60 FPS. Sprite animation is consistently inconsistent and is based upon which priority order we are using, how long it takes the sprite engine to execute, and when sprite engine execution occurs inside the 3 subframe window of time. This is a pretty big deal. Our example let an NMI handler slice through the writing of FF to unused sprite data stored in page 2. This could have been worse. Consider that fewer objects on the screen means that the sprite engine begins earlier. The logic for writing to page 2 will likely decrease in duration, and we are in danger of interrupting and corrupting the writes to page 3. In a similar fashion, more objects on the screen means that we start executing the sprite engine later. This means we may interrupt and corrupt sprite data written to page 2. We've seen the consequences of interrupting the sprite engine once before. By the way, our earlier example showcased our need to wait on the attribute update hammer. You can see that our level scrolled and our tiles for the level are in place when subframe B was rendered, but the colors of those tiles are incorrect. Fortunately, those attributes are updated between subframes B and C, and subframe C renders the tiles with the proper colors. Minor, but it happens. We could do an entire video about seams and background colors in NES games. But listen, here's the key takeaway for this entire video. Micronics' workload distribution across these 3 subframes is responsible for the game's feeling of jank. It isn't just about a low frame rate. Micronics used each NMI period to give them what we've got so far. This is convenient for programming, but disorienting for the player. Oh wait, I almost forgot. We ran Ghosts N Goblins at 60 frames per second earlier. How did that happen? Some value has to be responsible for making sure we allocate 3 subframes worth of time to game frame processing. That is what determines if and how long we need to have the CPU execute an infinite loop. This value is actually changed on the fly depending on which screen type we are viewing within the game. If we hone in on the value used for level gameplay, that value is 3. Well, if we change 3 to 1, we are no longer waiting on anything before outputting the next game frame. We just turned Ghosts N Goblins into Strider at triple the game speed. And yeah, I am using an invincibility code here as well, because of course I am. There are other non-Micronics games that control the frame rate in this same manner, but if we stick to Micronics developed titles, this means we can easily shove other games into 60 FPS mode, such as 1942, Athena, Tiger Heli, And Akari Warriors? So we have control over the frame rate of these games, but the requirements return us to basic needs. Optimize inefficient code, such as the Sprite engine, to shorten up game frame calculation time. Alter physics to fit with the new frame rate. On that note, it's worth mentioning that there is no gravity constant in Ghosts N Goblins. You would think altering velocity and the gravity constant would get you to jump at the proper speed when the game is running at 60 FPS. That would probably be true if those two things existed. Arthur's changes in pixels per frame come from a lookup table. There is no calculation on the fly. The total pixels traveled over a period of time are just baked in. So now what? Triple the size of the lookup table and work out the exact number of pixels for a jump at 60 FPS versus 20 FPS? Or convert the entire operation to use initial velocity with a gravity constant applied over time? That's a serious shift in math for only a single physics tweak. Changing physics also starts you down the road of bug fixes. For example, back to standard game speed here, you can run, press jump, and your jump continues in an arc. However, if you jump and then press a direction, you do not move laterally. This is apparent from the start as you encounter obstacles. Make sure you don't press jump before you press right. Anyway, I think we're done. If you enjoyed this video, please consider liking, subscribing, and leaving a comment. I also have a Patreon available if you are interested, and thanks for watching.